Hello, I'm Pablo, and I will be doing the first half of this presentation. Then Alex will be doing the second half. So, without cryptocurrencies, if you want to make a transfer through the internet, you need an intermediary like a bank. And a bank just basically just has a ledger with the amount of money that you have in your account. And when you do the transfer, you have to tell the bank, okay, now I have less money, and the recipient of the transfer has more money. And what cryptocurrencies do is they just distribute the ledger so that everybody has a copy of the ledger. And with that, we can essentially uh, overcome the need to trust a third party, to trust the bank. But this is not always enough. Sometimes you need to do other things, like, for example, exchange an amount of money in one currency for an amount of currency of a different currency. And you cannot just do two transferences, because then you need to one of the two parties has to trust the other party to do their bit. Whoever goes second will not just keep both of the parts, right? And that's what smart contracts are for. Smart contracts are basically like normal contracts, but they are written in the distributed ledger. And instead of being written natural language, they are written in a programming language. They are essentially computer programs, and they are not interpreted by a judge. They are interpreted by a computer. They are not enforced by law. They have to be self-enforcing. For example, a smart contract cannot force you to do something or to pay something, which is a limitation. But if you do transfer an amount of money to a contract, or for example, a token, then the contract can decide what to do with it. So it's self-enforcing in that way. The other thing is, because there is no judge, if you make an error when writing a smart contract, then there's no one that will interpret the original intention of that contract. The error will modify the contract, and that will be the consequences of the contract. So, for example, it can be that the money will end up going to the wrong hands, or even it can happen that the money will be destroyed forever. So that's quite bad. Also, so what do we do about this? The Marlowe language is a domain-specific language which is aimed specifically at writing smart contracts in top of cryptocurrencies. And it is very, very simple. So if you know Haskell, you actually can generate Marlowe smart contracts very easily, because Marlowe semantics are defined as a Haskell data type, which you can see in this slide. And the syntax and the semantics are defined as a function, a set of functions in Haskell. So it is very, very straightforward. In addition to that, so why do you want to use Marlowe instead of general purpose languages? And the reason is that general purpose languages give you more flexibility than you probably need for making day-to-day transactions or to making smart contracts. And with these possibilities, it also comes the opportunities to introduce bugs in the contracts. So Marlowe is good already because it reduces the number of possibilities, and it's also good because it is designed to be easy to read, to be clear, to be explicit, and to avoid most of the pitfalls that you can make. Well, the most common pitfalls that you can make while writing smart contracts, like, for example, forgetting to give a timeout for parties to do things. For example, for making a deposit. So if you don't give a timeout to a party, the party can decide to stall the contract, which can be can translate in a problem for the other parties. It can be leverage, and it can you can also forget, for example, to refund money if there is the contract is aborted, right? And all of this is enforced by Marlowe. Also, because it is limited in scope, we are able to actually statically analyze Marlowe contracts automatically. So you can say, for example, you can make sure that if a Marlowe contract says that it's going to pay an amount of money, we can statically analyze whether at that point in the execution of the contract there will be for sure enough money to make that payment. So we can ensure that Marlowe contracts keep their promises, right? And also we have developed an IDE, a web IDE, which we call the Marlowe Playground, which is what this presentation is about. And this Marlowe Playground allows you to create, to edit, to simulate, to analyze contracts. And both Alex and I will be using the Marlowe Playground from now on in order to demonstrate how Marlowe works, how to create Marlowe contracts, and of course, how the Marlowe Playground works. So give me a second to share my screen. Okay, so let me give you a tour of the Marlowe Playground. The Marlowe Playground has 3 tabs, which correspond to 3 different ways of editing Marlowe contracts. The simulation tab, in addition to letting you edit pure Marlowe contracts, it also allows you to simulate them here in the right side. So you have some examples you can load by clicking here on the top. So for example, here the escrow, you see that in the right side, it gives you the options that you would have for this escrow contract. Alex will show you more in detail how this works. On the bottom, you can see the state of the contract. You can see the static analysis tool you can use for the contracts. And you can see warnings, errors, and the log of the execution. And then it's also worth mentioning that you have the tutorial here. If you want to learn more about Marlowe, you'll find a lot more detail in here. Let me show you. Yeah. And also you will find these small blue buttons around the playground. If you click them, it will update this contextual hub, which will also tell you about the playground. The second tab, Haskell Editor, allows you to generate Marlowe contracts using Haskell, and Alex will also show you how to use this in more detail. And the Blockly tab uses Blockly to generate Marlowe contracts. And Blockly is this jigsaw-like way of creating contracts, of writing programs in programming languages. And I'm going to start by showing you the Blockly bit because I think it's the most beginner-friendly way of writing Marlowe contracts. So let's get hands-on. I want to show you how to make a contract that solves the problem we were talking about of exchanging money. So I'm going to write a contract that exchanges $1,000 for 12,000 ADA. The main building block of contracts is the contract construct, and you can find it here. There are 6 contract constructs that you can use, and they all execute immediately except for when. When is the one that takes input from users and the one that takes assets from the users. So we will be using when, pay, and let. If it is the same as in usual programming languages, it takes an observation, and depending on the observation, it will go through one branch or the other one. Observations are just booleans like in normal programs. You have true, false, you have combinations of those, and you can compare values. And values are integers, which represent amounts or times, slot numbers. And in general, Marlowe contracts have this structure. They are nested like this, right? And the thing that's at the top, the construct which is at the top, is the first one which is executed. And once that construct is executed, then it will be removed, and we will take one of the continuations to be the new contract. So it will keep going on, dismantling the contract until we are left with the closed contract, which is the only one that closes, that doesn't have any gaps, right? So once we are left with closed contract, the contract will refund all the money that it has, and it will terminate. As I say, let's go now and do a swap contract. So let's start by asking the participants to deposit the assets they want to exchange. In this case, we want Alice to deposit ADA and Bob to deposit dollars. So first Alice. So you can see that the when construct has a gap for actions. Actions is this construct here. We have three types of actions. One is for depositing assets, one is for making choices, and one is notification is for waiting for an observation to be true, right? Like this. You can plug it here. And you can also have several actions which are alternatives. So the participants can choose any of them. And you can also choose to have no actions here. And this will just act like a timeout. So if you say 100, this contract will just wait until the slot 100, and it will continue as whatever you put here. But let's put a deposit of ADA. So we want Alice to deposit ADA. We have two ways of specifying parties by public key. Or you can use role, which unlike public key is something that you can transfer because it's represented by a token. So let's use role. I'm going to call the role Alice. And then we have the amount of currency we want to deposit. And that's written with the value type. So let's use the constant. And I said we were going to deposit 12,000 ADA. And now we have to specify which is the currency. The currency is specified with the token construct. So we have ADA, very conveniently, and we have a different token, which is represented by two hashes, the currency name and the token name. But let's put ADA for Alice. And then we have to specify in which account we want to store the money. Accounts are represented by a number and an owner. In this case, we want Alice to be the owner of the account. The owner of the account says who is going to get the money when we reach close. So if by the end of the contract there is still money in this account, it will go to Alice. That's why we in principle want to say that Alice is the owner of this account. I've already written 30 here. This is when we expect Alice to deposit the money. If Alice hasn't deposited the money by slot 30, then it will continue here. And in this case, we just want to close the contract. But if Alice does deposit the money, then we want Bob to do the same. So I'm going to duplicate this and put it in, oh wait, we need another when construct. And this time for Bob, we are going to wait until slot 40. I'm going to put this inside. Now the role is Bob, and the amount is going to be 1,000, and we want dollars. And we don't have dollars, but we are going to imagine that we have a token which represents dollars, and its hash value is going to be 0000 and 85BB65FF. Wait, FF. And here we want to store it in Bob's account. Okay. Also, we want to close if Bob doesn't deposit the money. So notice here that if Bob doesn't deposit the money, we are closing. So the money of Alice will go back to Alice because we have deposited into an account which belongs to Alice. But if we make it here, then we know that the contract already has the money for Alice and Bob. So we can swap and give one another the assets they just deposited. So for that, we use the contract pay, which is very similar to deposit. First, we have to say who we are paying to. So first, let's pay Alice. I'm going to duplicate this again. And when we try to fit it here, we see that it doesn't work. The reason it doesn't work is because pay can also take an account as a recipient of the payment. So we need to use type payee instead. You can put an account here. But let's put a party, and then we put the actual role inside the party construct. Now the amount we want to pay Alice is the one that Bob deposited, so I'm going to duplicate this again. I'm using Control V to duplicate, which is faster. I'm going to duplicate the type of currency as well, and also the account from which we are paying, which is Bob's account. And we do the same for Bob. This time we pay Bob, and the amount we pay is this. And this time we pay Ada, and we pay from Alice's account. So that's it. Now we can close the contract, and we are done. We can now actually extract the actual Marlowe contract from here by clicking to code, and this brings us to the simulation tab. We can see that here we would be able to simulate the execution of the contract, and we are already being prompted to deposit by Alice 12,000 ADA, and if we accept that, then we are prompted to deposit 1,000 by Bob, etc., etc. One thing you may wonder is, how do we know which construct we're using in which gap, right? For example, here I had some trouble because I did in principle try to fit a role in a party, and we have 8 types of constructs in Marlowe. So this is trial and error is a bit time consuming. But there is another way of building Marlowe contracts which doesn't require you to know what goes in which gap, and that's called holes. So notice that if I try to convert to code a contract which is incomplete, where we had gaps before, now we had a hole, which is this string which starts with a question mark. Notice that the editor has already found that there is something incomplete here. If you click here, you see found a hole of the type PE, which is the type we are looking for. And if we click quick fix, we get all the possible constructs for that type. So in this case, we wanted party, and we can do the same. We can actually build the whole contract by doing this. For example, here we have either public key or role. So if we click role, we will get this role token. And here we had a default string that was filled for us, but here we actually wanted Bob, I think. Also, we can switch between simulation tab and Blockly, like I said. So you can click here to go back to Blockly. So you can use whatever tool you want to use at each point. Okay, so let me show you some more of the functionality of Marlowe, and let's make this contract a bit more complicated. Let's say we don't want to specify how much money Alice and Bob want to exchange. Let's let Alice and Bob decide how much. We can do that by nesting this forward. Let's move this to a side temporarily. Let's put another when, but this time we are going to ask for a choice. So this choice I'm going to call Alice's choice, and the choice owner is going to be Alice, which is who is making the choice. And for choice bound, we are using the bound type, which just says between which numbers Alice has to choose from. So let's say between 100 and 10,000. And let's give until slot 10 for making this choice, and if not, we close the contract. Let's do the same for Bob. Let's give both a chance to have a say. And we call this Bob's choice, and the role is Bob in this case. And let's give until slot 20. Now, let's calculate what is the minimum they have agreed on of amount of dollars to exchange, and use that to calculate the actual amount we will be exchanging. So for that, we are going to use the let construct. And I'm going to call this the amount of dollars. Now the amount of dollars, we want it to be the minimum of these two amounts. So for that, we calculate a value and we use the if then else, which is of type value. And we want to say if the amount by Alice is smaller than Bob's, then we use Alice's amount. If not, we use Bob's amount. And to reference to the choices, we use this other value construct, which is called choice blah. Choice, in this case, for example, Alice choice by Alice represents the value chosen, and it has a default value in case it hasn't been chosen, which in this case is impossible because we are in a branch where it has been chosen. So let's just put constant 0 here. And let's do the same for Bob's choice. Bob. And now we can compare both of the values by using the observation value is less than. So if Alice's choice is less than Bob, then we put Alice, otherwise we put Bob. So I'm going to put them in reverse order with Alice and if. And we put this here. So this gives us the amount of dollars. And now we can use this amount of dollars to calculate the amount of ADA. And we can do this by using let again. And here we say amount of ADA. And in order to make we make a reference to this amount of dollars, we use the value use amount of dollars. But we don't want it to be the same. We want to have a conversion rate, and we do the conversion rate by using the scale combinator. And I have calculated this to be 15,081 over 1,250. So now we have the amount of dollars and the amount of ADA. I'm going to get uses for all of them. Amount of ADA. So here now we can replace the amount of ADA for the variable. Also here, sorry. And the amount of dollars for the value. And we can put the rest of the contract back. So that's it. Now we have our more interactive contract. And if we send it back to the simulator, we can see that now the first thing that happens is that Alice is asked for a question. So we can put here 2000, for example. And we can imagine that Bob says 1000. And the contract automatically calculates the amount of ADA that Ali has to put and the amount of dollars that Bob had to put. So that is basically it. Now Alex will explain how to use static analysis to ensure that contracts behave the way they are supposed to behave, and he will also show you how to use the Haskell editor to generate contracts.